Hello guys, now in this part I'm going to move away from the discussions on control subjects, but to talk about sensor and measurement systems. And of course, sensor and measurement systems can be a very important part of a control system because we rely on sensors or measurements to provide us with the necessary feedback for the closed-loop control. Without feedback, control won't work. So they are a very important aspect of a control system. But on the other hand, sensors and measurement systems, they have many other different applications. For example, in condition monitoring systems, where you want to make sure something that is in a good health and working or functioning as expected. So you need some kind of devices to tell you what is going on. Okay, so they have fairly wide range of applications. To start with, I want you to actually look back into two old measurement devices and think about what is actually behind these devices. On the left-hand side, we have a old thermometer, which tells you the temperature of the environment. Now, if you think about that kind of device, basically it relies on the property of a special metal or the only liquid metal, that's mercury. So it relies on the property of mercury and their sensitivity to temperature, because when the temperature goes up, the mercury expands, so the volume gets bigger. So what you have here is a little bit of container there where the mercury is stored. If the temperature goes up, mercury expands, so the mercury goes up through that very thin tube. If the if the temperature drops, then obviously the volume of the mercury reduces and the level of the mercury also drops. And then, of course, you have to calibrate and make sure you have these scales to show what exactly the temperatures are. Okay, so in this particular device, you have a sensor, that's the mercury, basically. You want something that's sensitive to what you want to measure. And then, of course, that is converted into a expansion and a format. So because it changes, the volume changes with temperature. So the change in temperature is converted into change in volume of the mercury. And then, of course, they have the display unit that has to be calibrated to give you the right readings. So this is the process, the sensor, the conversion, and display. On the right-hand side, I have a very old voltmeter that measures the voltage. Now, if you think about the principle of very old voltmeter, this is how it works. You have a coil, and you apply, if you connect the terminals of a voltage you want to measure, then of course that voltage produces a current in the coil. The coil produces a force against a magnet. Now, inside a magnet, so it's a magnetic reaction force. Okay, that works against a spring installed to the needle. So if the current is high, or if the voltage is high, the current will go up. Therefore, the force produced is also high. That pushes the needle against a spring a bit more. If the current reduces because of lower voltage, then the force is reduced. Therefore, the spring pushes the needle back. Okay, and of course you need a display, and that display needs to be calibrated to give you the right reading. Okay, so in this, the voltage produces current, The current produces a force. The force works against the spring. And that determines the position of the needle, which tells you the voltage. So in this scenario, the sensor is a coil, but it converts the current or voltage into a force and then converts that into a movement. So there are two stages of conversion there, okay? And then you can display that. So in the olden days, you don't really you don't think, sometimes people don't think twice about it. It works. And there's, probably you probably have a vague idea about how it works. And some devices can be very cleverly designed. But that's, that system modeled together is a single device. You can't really take anything out of it. It's there, you can read it, but nothing else you can do with this. Modern devices are different. If I look at an example here, this is a multimeter of a modern voltmeter, a multimeter. Actually, it can do all sorts of things. It can measure current, it can measure voltage, it can measure resistance, you can measure temperature, or all sorts of things, because the principle behind it is quite different now. Now, what we have nowadays is that you have a sensor that tends to convert. There's also a conversion process, okay? That tends to convert any quantity you want to measure into a voltage or into a resistance, okay? Now, that voltage gets amplified and processed with a computer. And then the computer will send numbers out for display. So what you see here will be the numbers, but inside of this process is quite a complex processing unit. Sometimes, maybe old multimeter don't have a computer inside, but it will have some electronic circuits to deal with different signals or different sensor inputs. So the principle behind it now is becomes fairly standard. It's not unlike the previous case where every device will have probably different working principles. Okay, so nowadays it's fairly standard, although the technology involved will be application dependent. Sometimes you want higher precision, sometimes you want more higher working range, that kind of stuff. But so design can be different, but the general principle can be quite a standard. Of course, the sensors will be different. Okay, but in general, this a measurement system or a modern measurement system will consist of two very important parts. One is a sensor. It's what kind of sensor you use. That's take the measurement. The other is the data processing, how you process the input from the sensor. Okay, so there are two aspects of it, and therefore I'm going to divide this topic into two parts. So I'm going to talk about sensors first, and then talk about processing, or data processing, the ways that we can actually process data. And of course, because we have a limited time, we can't really discuss everything. So I'm going to pick some fairly representative sensors, and then talk about some fairly typical ways of people dealing with data processing. Okay, two separate topics, but they are equally important. So I'll start with sensors first. A lot of sensors or sensors that use different principles but to convert the quantities what you want to measure into a voltage output. This would be one of them. It uses a potentiometer to measure the position or measure the movement of some object. Okay, so the idea is it's quite straightforward, because if you think about the potentiometers will have three terminals, and there's an overall resistance. This is R. Okay, and if you apply a constant voltage to the overall resistance, and then you have a constant current going through that resistance. Okay, the current will be constant. And then there's a third terminal. That is actually a sliding thing that actually moves up and down with position. So inside of that tube, you have this terminal. Okay. Now, if you think about that terminal there divides the overall resistance into two parts. Above it is above it is R1. Below that point is R2. So between R2 and this term, the active side of input voltage, you have output. Output voltage will be dependent on the R2 value, because the current is constant. So voltage VO equals R times I times R2. R2 is dependent on the position of that third terminal of the slider. Okay, so as this thing moves up and down, and R2 changes with different position, therefore the output varies with different position. So basically, output will give you the idea where you are in terms of the displacement movement. Okay, everything else is fixed. The only variable here is this slide, the position of the slide, and therefore the output voltage. So there's a set of equations that I can show you. So this is second part is R2. Current equals to Vs over R, that's overall input, divided by overall resistance. Output voltage equals to the current times R2. So that's current times R2. Therefore, if I substitute equation number 1 into number 2, I get I equals to Vs over R, that's Vs over R times R2. Therefore, it becomes R2 over R times Vs. Okay, that's my equation number 3. Now, obviously, when this slide moved all the way up to the highest point, or the maximum displacement, R2 will equal to R. So that slide moved to this point there, R2 will equal to R. Therefore, VO equals to Vs. Okay? And because that relationship, X therefore, because that relationship, X therefore will have a relationship like what's defined in equation 4, because I can do this. In equation 3, I can divide Vs to both sides, VO over Vs. VO over Vs equals to R2 over R. Okay, the displacement also give you, this is a maximum resistance. So if you think about maximum resistance, it's where you move to. There, that reflects to R. So Xm represents the maximum displacement. That corresponds to R. And any position in between corresponds to R2. Therefore, you have X over Xm equals to R2 over R, that relationship. Consider equation number 3. R2 over R, as I said earlier, if I divide both sides by Vs, then R2 over R equals to VO over Vs. Therefore, I can replace this R2 over R by VO over Vs. So this X over Xm will equal to VO over Vs. Therefore, VO equals to X over Xm times Vs, or I Okay, reformat that equation. X equals to xm over xvs times VO. Okay. Now, if you look at equation number 6, we know what we applied as input. Okay, we want to keep that constant. We know the maximum movement of that potentiometer because that's what you designed it for. Okay, and it depends on what your requirement is. And then, of course, okay, if we measure the output voltage, then we will know how much displacement we get. So in this case, the voltage here is proportional to the displacement. So we converted a displacement into a voltage. So most analog signals will give you a voltage output that is proportional to the quantity that you want to measure. Which of course is good news for computers because computers can take that voltage in. The way it takes in, then we can talk about that later. Okay. A different device, but we'll give you something fairly similar. It basically measures the absolute acceleration of an object and convert that into a voltage. Okay, well, it converts into displacement first and then converts that into a voltage. It may be a very tiny bit of voltage. It can be a very small voltage, but the voltage will vary with acceleration proportionally within a frequency range. Okay, and of course, even though the signal may be small, but we can deal with that signal in the second part, the signal processing part. Okay, but that's for discussion in the next part. Now, the measurement of acceleration is achieved from that little thing. It's really quite small. You can see I've got a coin there, what we call accelerometer. It's quite small. It's actually attached, if you want to, it is attached to the surface of the object that you want to measure. So over there, that represents the surface. Okay, it can be any surface, can be a flying object, or can be a car or something. If you want to measure the acceleration of that surface or this object, you attach a device like that onto the surface. Okay, inside the device, there's a little mass. Okay, a small mass there. It's a little mass there. And the mass is connected to the case of the accelerometer through a little spring. Now this little symbol represents the damping there. Okay, because even though it's a spring, all spring, because they are made of some metal, and metal will have certain damping properties. So there's some damping values in there as well. Okay, so you can consider this is connected through a spring and a damper in parallel to that little mass. As the base or your surface vibrate, moving up and down, of course, the spring and the damper will produce a force that acts on this mass to start to move. Therefore, the relative movement or relative displacement between the mass and the case where you mount. Remember, the case is mounted onto the surface, so it's really the displacement between that little mass and the surface of the object you want to measure. That distance, that change in displacement is actually converted into a voltage via a device sometimes called a piezoelectric device. But the principle it lies behind this is this. The key is how come this relative displacement can be used to indicate the acceleration of the base or of the object. So I'm going to apply the Newton's law to that little mass there. Okay, so F equals to ma. F is a force. Force, if you think about that, that is a flow. It's a free body, a free mass, but only the connection we have here is a spring and a damper. The spring force produces force as the two objects moves. The little mass moves, the base moves. The force in the spring is proportional to the relative movement of the base and that little mass. So the spring force equals to K, that's the spring constant, times X object. This is what we want to measure. Okay, that's the object we want to measure. That's X, that's displacement, minus XM, that's the movement of that mass, plus the force in the damper. Now, the force in the damper is proportional to the relative velocity of the motion between the two objects. So it's B times X object, that's object, dot minus XM dot, which is XM dot. B is the damping coefficient. That equals to MA. A is the acceleration of that little mass. Okay, not acceleration of the body yet. Okay, this is the acceleration body is what we're trying to get to. And so that's F equals MA. That equals MA here. But I'm going to change the format a little bit there. I'm going to add minus X object double dot into the bracket. So this becomes XM double dot minus M times X double dot object. And you will say, yeah, of course you can't do that because, yeah, no, I can't do that. But I will cancel that out with another thing. Okay, so I added a minus M times X object double dot, and then I'm going to add a positive M X double dot. Now they are the same. Okay, now the reason why I'm doing that is because I have relative displacement here, I have relative velocity here, so I want a relative acceleration and absolute acceleration of the base. This X double dot object is what I want to measure. Okay, so if I say X is the relative displacement, so X equals to X object minus XM, this is what this little device try to convert. Okay, so the output voltage will be proportional to this X. So this will be the X, this will be X dot, this will be minus X double dot because the signs are different. Okay, but I can move this term to the left hand side, then it becomes positive. And then divide M to both sides as well. This is the equation I end up with. So relative the acceleration plus B over M times relative velocity plus K over M relative displacement equals to absolute acceleration of the object that I want to measure. So there's a relationship here, okay? And relative displacement that I can measure with VO. Now, if I apply the Laplace transform to that, okay, this side, this is the acceleration of the object. Okay, it was XM double dot, X object double dot on the previous slide, but that's really a object. So if I apply Laplace transform to this equation, this becomes S squared XS. This becomes SXS. This becomes XS. This becomes object S. Therefore, the relative displacement, if I take the common terms out and reformat it, this is what I get. The relative displacement is some transfer function times the acceleration of the object that we want to measure. Okay, now this transfer function says, well, actually, it's not necessarily going to get it every time, but depends on the selection of the values, we can actually make this transfer function to give us a fairly flat, fairly constant value in a frequency range. That means it will work for certain frequency range, but outside that frequency range, it probably won't. Okay, so it depends on your design. So you have to select that M, that K, and that B value to make sure it works in that frequency range. Okay, so in this case, I did some selection there, and you can see at lower frequencies, perhaps up to 200, 300 radians per second, the output response is, well, the frequency response is flat. That means the response for the output will be the same for different frequencies in that frequency range. So a sensor like that would probably work, will or should work in that frequency range. Okay, it's not going to be catch-all, so you can't possibly have a sensor like that without working for all frequencies. Okay, but we don't need them to work for all frequency anyway. Okay, every system will have a bandwidth, so that's kind of stuff that we need. And that's how accelerometer work. Okay, but essentially what you also get behind all this theory is that you get output voltage that is proportional to the acceleration of the body that you're trying to measure. Okay, this device is very similar. It measures the temperature, but it doesn't involve any mercury anymore. Okay, it's basically works on principle. It's fairly some physics where if you put two different metals at a joint, and then the temperature causes a change in the output voltage. Okay, and of course, when the voltage changes with temperature, then you can use that signal to measure the temperature. Okay, it's called thermocouple. Okay, another device will be it will be working in a very similar way that will give you the similar kind of output, but the range of the output, sometimes they give you a voltage range that's quite easy to handle. Sometimes they give you small voltage, or sometimes they give you a voltage that is biased. Okay, but that's the stuff we need to discuss in the second part, how to deal with different voltages. Okay, and that's another sensor, or another sensor of a type of sensor, and it actually works. Try to give you a voltage but through a resistance change. What this device has is that it changes with the strain or the stress it experiences on the surface. And it is typical to measure the pressure or stress a surface can sustain or is sustaining. So you attach or you kind of glue that kind of device onto a surface. If the surface bends due to the flash, any surface will bend under stress. If you push on a hard table, you may not feel it, but there will be a very small bending mechanism there. Any metal surface, surface, if you glue a strain gauge like that onto it, and if the surface is under some kind of stress, then you will get a change in resistance of the strain gauge. Okay, now if you feed a current through the strain gauge, because the resistance change, if you feed current through it, then of course the output will be a voltage. Okay, it's tiny, that kind of device. It's a strain gauge, or they call it strain gauges because they are used to measure strains. Okay, but essentially here is that it changes resistance in the strain gauge as the stress level changes. Okay, whether it bends one way or another. So if you just imagine yourself, you have a strain gauge mounted on the surface of a metal strip. If the metal strip bends one way, it increases resistance in the strain gauge. If it bends in the opposite way, then it reduces resistance. Okay, so the resistance in the strain gauge goes up and down with the level or with a small bending mechanism, or how much stress it is under. But of course, there are also a different kind of sensors called digital sensors. And that gives you zero and ones, like this one. This actually is called a digital position encoder. And it measures the rotational movement. You can have the linear equivalent of these sensors, but this one diagram here shows you the rotational movement. What you have is a disc there. The disc is mounted into a shaft of some rotation system that you want to measure the angle or measure the movement. Okay, on that disc, you have two channels or three channels, two main channels that's been sort of carved out with slots, so you can actually see through from one side to another. Now they're carved up with a lot of slots. And then what you have, we use some kind of infrared emitter on the one side, is a device that shines light through. And then on the other side, we have something called the transistors that pick up these lights. So as the disk rotates, because we have slots that's carved out, so when the lights get through these slots, every time the lights get through, the emitter, the phototransistor picks up that signal, and then it's blocked when it's moved away from slot. And then from the next slot, the phototransistor will pick up a signal again. So basically, it's like an on and off switch. When the light is received by a phototransistor, it's 1. When the light is blocked by the disk or the other part of the disk, then it's 0, and so on. And typically, you get several hundreds of these per revolution. And there are two channels. There are two channels of that typically, and these two channels they are not really in the same position. The slots, they are shifted by 90 degrees. So the signals, highs and lows you get here, say for example, the signal channel A will give you a high here, but 90 degrees later, the B will give you a high there, and then a low here, a high there. And the advantage of using two channels, there are two advantages. One, you can determine the direction of the rotation by which side gives you high first, or goes from high to low, high to low. If it's rotating the other way, then this channel B will give you a high first. Okay, so you can determine which direction it rotates. And also you can increase the number of pulses, because you can not only count zeros and ones of one channel, you can count the difference between the two. For example, here, this is 1, this is 0, this is 1, 1, and this is 0 and a 1. So you're dividing one slot into 4 possibilities, okay? Therefore, you can increase the accuracy by 4 times. And the disadvantage of this disk is it tells you the rotation and how fast it rotates, because you can count the number of zeros and ones per unit time. That will tell you how fast or how slow. So this kind of encoder tends to better used to measure velocity or rotational speed rather than the position, because it doesn't really tell you where the position is. So to partially compensate that problem, we have a third channel. This third channel only exists it only happens once per revolution. So you only have one slot assert channel. So that gives you an index. Say, right, now this is the start of your next cycle. So once you get there, you can actually correct yourself. Okay? So think about this. This is two channels. You get high and lows because these slots, the noise gets through or not able to get through. Okay? And that in combination with that gives you the pulses as you rotate or as the shaft rotates, and counting the number of pulses per fixed time will give you the velocity, but it doesn't give you the absolute position. It doesn't really know where you are until you get that index. But that only happens once per cycle. So really, if you're in the middle of a cycle, it doesn't really help. Another type of sensor to overcome this problem is called absolute encoder. Now, in this case, we need a lot more than 3 channels. And on this disk, this actually shows the other side. You look at a disk from the side. Okay, so I have this example. I have 4 channels. Okay, on the very outside channel, and the disk is divided into 1, 2, 3, 4, 5, 6, 7, 8 different slots. So you have this part carved out, this part carved out, this part carved out, and this part carved out. So the light can shine through from here and there and there and there, but it's blocked there or there or there. Then just next to it inside, that divides a circle into 4 sections. So you have 90 degrees there, 90 degrees there, 90 degrees there, 90 degrees there. And then I have another one that divides the circle into 2 sections. I have half there, half there. Now, 3 channels. Did I say 3? Yes, it is 3 channels. Now, 3 channels will give you an idea where I am up to 45 degrees. Because if I'm here, no light gets through, I get 3 offs or 3 zeros. That's my 45 degrees. If I'm there, somewhere there, that gives me 0, 0, 1, or off, off, on, that's 45 to 90 degrees. If I'm there, that gives me 0, 1, 0, that's 90 to 135, and so on. But essentially, I know where I am, or which 45 degrees I am in. If you want to have better than that, then you need to add a channel outside to divide this by 16 parts, by a whole cycle into 16. That'll give you idea which 22.5 degrees you are in. And if you want better, you add another channel on outside that give you divide that by a further 2 and so on. So basically you need a lot more channels. And then probably, obviously, mechanically, it would be more difficult to do and more expensive to produce a sensor like that. But the advantage of that, you can't miss. It will tell you where you are exactly. You can give you the modern position encoders or absolute encoders can give you something like 10 digits or 12 digits. So it can be very accurate as well. Okay? But you need more channels. Therefore, more interface with computers. So that's really kind of sensors we want to talk about, and they are fairly representative, but they are not exhaustive. Okay, I can't possibly go through every possible candidate, but hopefully I covered enough so you've seen the basics of different sensors. So in the next part, I'm going to talk about the signal processing out of